Welcome again to another action-packed episode of Empowering Introductory Algebra. Hi, I'm Bob Young, Assistant Professor of Mathematics at Brevard Community College. Along with my excellent support staff of WBCC, we continue to bring you top-notch algebra lessons that you can work on anytime convenient to your busy schedules. Let's continue our journey. Now, in the last episode, we've been working on radicals and simplifying radicals and so forth, and we're going to continue with some radicals today. Going to our graphic, we are going to talk about addition and subtraction of radicals. Did you know that like radicals have the same radicand, and if they have the same radicand, and remember that's the part that's underneath the radical, they may be combined using our friend the distributive property. So let's go to some examples of that. And in the first example here, we have 4 times the square root of 7 plus 6 times the square root of 7. So notice they have that commonality there, that common square root of 7 there. So we can go ahead using the distributive property. Now, we usually don't go through all this process when we do this, and write it in this manner. 4 plus 6 times the square root of 7. It's almost like you're taking out or factoring out that square root of 7 to give you a final answer of 10 times the square root of 7. So whenever those radicals have the same radicand, you can combine them just by, maybe you could even think of these as coefficients like in variables and get that final answer. All right, next one here, 8 times the square root of 3 minus 12 times the square root of 3. 8 minus 12, negative 4 times the square root of 3. So isn't that nice when those radicals are the same there? You can combine the numbers in front to get the final answer. And don't let them scare you with variables. If they throw the variables at you, remember variables are just numbers in disguise. So you have 10 times the square root of a minus 4 times the square root of a minus 6 times the square root of a. Now wait a minute, young. Some of you are going, what's up with this one? What's 0 times the square root of a equal to? Well, remember, anything times 0 is what? 0. Yeah. So that multiplication property of 0 even holds when you multiply 0 by a radical. And then if they really try to get nasty and put a mean, vicious-looking radicand, are you going to be scared? Scared? Not scared. Scared? All right, no. You're going to have 5 times the square root of xy minus 6 times the square root of xy. Just take those numbers in front. 5 minus 6, negative 1. Will they put the 1? Probably not in most textbooks. If you put a negative 1 there, that's fine. So when those are nice radicals and they have the same radicand, you can combine them. All right. Let's go to our next graphic, though. Is everything always that easy? No, young, you know that. Unlike radicals, or a combination of numbers and radicals may not be combined. All right. So let's go look at some of these. Go back to the examples here. Now, we can't take the square root of 45 and the square root of 20 and combine them. Why? Because, well, gee, they don't have the same radicand. So, what are we going to do? Well, let's see if these will simplify. And I bet you they will. Why? Because this is addition and subtraction of radical section. So the square root of 45, if you break it apart and find a nice perfect square number that breaks 45 apart, remember? Using the product rule, the square root of 9 times the square root of 5 gives you the square root of 45. So this one simplifies into a nice 3 times the square root of 5. So we get some more practice simplifying radicals. The square root of 20, what nice perfect square number breaks 20 apart? Yeah, 4 times 5. The square root of 4 times the square root of 5 gives you the square root of 20. And then, guess what's coming out of the radical here? Right. The square root of 4 is 2 times the square root of 5, and oop, looky there. There's those nice like radicals again. So sometimes they'll try to give you some unlike radicals. You make them like, and then you use the rule. So how many square roots of 5 we ended up with? 1. Yes, 1 square roots of 5, which I'll just write the square root of 5. All right, and here's another one here with numbers and radicals and all kinds of good stuff here. Now, young, which one of these would I pick on here? I'm going to go pick on the small radical. You know, so pick on the little guy. Pick on the easiest one. If they give you a string and these look kind of intimidating to solve here, let me show you a way to cheat out there, and it ain't cheating if you're smart. The square root of 8, I think y'all out there would say, well, that's a nice one. That breaks apart into the square root of 4 times the square root of 2. Now, don't forget that 9's out front of there. Some people leave that hanging, and it'll be, All right, so anyway, the square root of 4 is 2, and that comes out of the radical times this 9 here. So this first part simplifies into a nice 18 times the square root of 2. All right, now, if this one's got a square root of 2 in it, and this is the addition and subtraction of radicals, and they don't make them all like, and this one's got a square root of 2, maybe all of these will have a square root of 2, Young. I'm going to cheat. And I know some instructors out there are going, wait a minute, you can't do that, but watch me try. And it works a lot of times out there, you students. So I'm going to slip a square root of 2 on these other guys. 2 times what gives me 72, and oh, looky here, a friendly 36. Yeah. 2 times what gives me 98? A friendly square root of 49. So remember out there, it ain't cheating if you're smart. So now you've got what? Minus 6 times the square root of 2 plus 7 times the square root of 2. So all of these unlike radicals we made like. Now, how many square roots of 2 when we put them all together? 18 minus 6, 12 plus 7? 19 times the square root of 2. Final answer. All right, so feel that radical power surging in your veins. All right, now, even ones with variables you can do this process with. Let's cheat again. Gee, I wonder which one of these looks easier to do. Pick on the little guy. Yeah, pick on the little guy. That's not nice out there. So the square root of 4a, what's coming out? Y'all see that square root of 4 comes out as 2. That square root of a is left in the radical, so this one simplifies into 2 times the square root of a. Now again, if this one's got a square root of a, I bet you this one will have a square root of a in it. So watch me cheat, or it's not really cheating, because a times what gives me this? Oh, a nice 81a to the what power squared? Or should I say a friendly 81a squared, because that comes out as 9a times the square root of a. So now we've got those like radicals. Now some of you are looking at this go, wait a minute, Young, I can't put those numbers in front together. They're not the same. I mean, those aren't like terms. I can't put them together. So what do? Well, you use that distributive property again. So here's how they write it. They do put these together. They just write 9a plus 2, put that parentheses around it there, times the square root of a. So even if the items in front are not like terms, you can still write the answer and then put that like square root there. What do y'all think? Not too bad. All right, fractions, you ask? And people are going, no, Young, I can't take it no more fractions. Yes, even these guys have fractions. Now, what's wrong with this is we can rationalize the denominators here. So first off, we can't have radicals in the bottom, so I would say take Mr. square root of 2/3 and multiply top and bottom by the square root of 3 over the square root of 3, because we can't have that we have to rationalize that denominator. And what does that give us? Well, it gives us a square root of 6 over 3. All right. Second one, multiply by the square root of 6 over the square root of 6. Now these are already simplified, so we end up with minus the square root of 6 over 6. All right, now we went ahead and rationalized the denominators on these. Now, how do we add and subtract fractions? Well, to add and subtract fractions, whether we've done variable ones, we've done number ones throughout this course, even ones with radicals, you need the coveted common denominator, which I don't think will blow anyone's minds out there. It'll be 6. So the first one gets multiplied by what to get this common denominator? 2. And if you multiply the top or the bottom by 2, you got to do the top by 2. So we end up with 2 times the square root of 6 over 6. I like this second fraction. It's already got that denominator, so it stays the same. And notice, even with fractions, if we have that like radical, 2 times the square root of 6 over 6 minus the square root of 6 over 6, we end up with 1 times the square root of 6 over 6. So you can even perform operations on fractional radicals. Simplify, rationalize the denominator, get that common denominator, put them together. Put them together. All right, now let's go back to a graphic here real quick. And this one's really you guys are just gonna love this. More multiplication. Did you know you can distribute radicals? How about multiplying by foiling? The answer to both questions? Yes. Let's look at some more examples here. So we're going to go back and do all kinds of fun stuff. So here's our friend, the distributive property, all kinds of radicals in here. We're going to multiply the square root of 3 times the square root of 3. And remember, any square root times itself, 3. The square root of 3 times the square root of 2. When you multiply radicals, you get a radical, and that's a nice simplified one. So stick a fork in that one, it's done. All right. The next two here, we've got a what? Whenever we multiply binomials in algebra, we have learned to FOIL. FOIL or be FOIL. So you can even do this with radicals. So the first two terms, 2 times 5, 10. The outside two terms, 2 times a negative square root of 7 is minus 2 square roots of 7. The inside two terms, one's closest together, 5 times the square root of 3. Both of these are positive, thus positive plus 5 times the square root of 3. And the last two terms, when you have the square root of 3 times the square root of 7, positive times negative, you get minus the square root of 21. So some of these FOIL problems here, you have to watch out. Now, once you do all this, are there any of these radicals that simplify? Well, in this case, no. There's no radicals that simplify. There's no perfect square numbers that come out. Or are there any radicals you can combine together there? Well, no, because they all have different what? Different radicands. So in this case, when we FOIL, that was the final answer. All right? And you can even FOIL our friends, the conjugates. So the conjugates are back. Now let me go to the camera here real quick. And y'all remember I said way, way back the conjugates would be your friend. Well, today they are. They're going to be your friend, and they're going to help us to do some real interesting rationalizing the denominators problem. And we're going to have to attack it with our friend the conjugate. So let's go back to the examples here. And remember, whenever you FOIL conjugates, FOIL goes to Florida. The O and the I will go out. So when you FOIL conjugates, the first two terms, 4 times 4, 16. The square root of 5 times negative square root of 5, minus 5. So is anyone out there surprised to see I get a nice 11 out of this? I multiplied some binomials with radicals in them, came out with a nice number. Let's check here. Oh, even ones with 2 radicals times 2 radicals. These are conjugates. Why? Because one sign is different on one term here. So FOIL goes to Florida. And the square root of 10 times the square root of 10, we could think square root of 100, but 10 pops out. Positive square root of 3 times negative square root of 3 minus 3. Isn't that nice? 7. How about that? Hot dang. All right. Now, where is the conjugate going to help me, Young? Where is it going to help me? Now, look at these bad boys here, rationalizing the denominator with more than one term in the bottom here. All right, and we can even make this, let me make this one the square root of 3 plus the square root of 7 with 2 radicals, and then we'll have a contrast down here with just 1. Now, if I tried to just multiply by the square root of 3 over the square root of 3, it would take this one out, but I'd still have a radical in the bottom. Or if I just did the square root of 7 over the square root of 7, it would take this one out, but I'd still have a radical when I distribute it in here. So our conjugate friend will help me rationalize the denominator with these ones with more than 2. So if you know what the conjugate of the square root of 3 plus the square root of 7 is, which I think most of us have seen throughout this course, the square root of 3 minus the square root of 7, it will take out both radicals in the denominator, and you will feel the power. You will feel the power on here. All right, so let's go to the graphic to reinforce that real quick, and you can get this down in your notes. So notice here it says if the denominator contains 2 terms involving a radical or 2 radicals, multiply by 1 outside the radical by using the conjugate of the denominator. So we like to go to these graphics and make sure that you got some good notes and some good things to go on. All right, so y'all got that? Let's head back to that example. Now, what's 1 mean? Multiplying by 1, that means whatever you do to the bottom of some fraction, you must do to the top. So there's my 1. That's when I say when I'm multiplying by 1 what I'm talking about. All right, so watch what happens down here. FOIL goes to Florida. The square root of 3 times the square root of 3, 3. Square root of 7 times minus square root of 7, minus 7. And what comes out? Woo! Both of those radicals toodles, you get negative 4. Yeah. All right. Now, what do I do with the top here? Well, I've got a 5, so I guess I can write this like 5 times all this here. And I suggest you watch out here because sometimes that number will go into the number in the top when there's numbers here. So watch out if that number here will cross-cancel or, chop into the top. It won't. So we can just go ahead and write the final answer. I'm going to have to scrunch it here. Forgive me. 5 times the square root of 3 minus 5 times the square root of 7 all over 4. So I just went ahead and distributed that through. All right. Could probably write that down here a little better, but I think you all got it. I'll make more room on this one. So another one like that, what's the conjugate of 2 minus the square root of x? You betcha. 2 plus the square root of x. And whatever you do to the bottom, you must do to the top. So even with variables, do not get intimidated. They're treated just like numbers because they are numbers in disguise. So again, when I FOIL conjugates down here, I'll do the old FL. 2 times 2, 4, minus square root of x plus square root of x, minus x. The top, I'm going to just go ahead and distribute that 8 through, and I'm going to get 8 times 2 is 16 plus 8 times the square root of x. Now, how's that looking for an answer? That is the answer. Rationalizing the denominator. All right, so now let's go to the next graphic. The next topic of discussion, solving square root equations. So we've got 5 steps here, 5 steps. 1, whenever you're solving a radical equation, and remember the equations have the equal sign in them, 1, isolate a radical on one side of the equation. 2, square both sides of the equation. 3, and I don't know if we're going to hit any of these in here today, but if a radical still appears in the equation, those are the real fun ones. Repeat steps 1 and 2. 4, solve the equation for the given variable. And 5, check and make sure all answer or answers check back in the original equation. Remember that no radical with an even root can have a negative radicand. You can't have a negative under that radical or it won't make sense. All right, so let me look at the camera here real quick. Now, we talked about what the square root does. What is the square root's purpose? It takes out the square. The square root takes out the square. They are lethal enemies. Now, you know what, ladies and gentlemen? Not only does the square root take out the square, but the square, guess what? Takes out the square root. So let's go to some examples and look at that concept. All right, so we've got the square root of x plus 2 equals 5, and I want to solve for x. So what I'm going to do is square both sides of the equation. Remember, when you have equations, the old BS is back. Both sides. Whatever you do to one, you must do to both. Now, when I square that square root, takes it right out. It means it's like multiplying by 2 of them. Whatever's under there comes out equals 5 squared is 25. So you got a nice little mini equation set up here. Subtract 2 from both sides, and you end up with x equals 23. Now, will that check back in my original equation? You're darn tootin', check this out. 23 plus 2, square root of 25, gives me 5. That answer will check. Yeah. All right, now second example, they don't have the square root isolated, all right? So we want to isolate that radical. How? We want to subtract 2 from both sides. All right, so make sure before you do the squaring process here that you get that radical isolated. So now we're going to have the square root of a minus 3 equals what over here? 4 minus 2 is 2. All right, so to take out the square root, you know what its archenemy is? Square both sides of the equation. Yeah, once you get it isolated. So a minus 3 then pops out of the square root, because when you square it, it takes out the square root, equals 2 squared is 4. 2 times 2. Now, how do I get a by itself to take out subtraction? Add 3 to both sides. So a comes out to be lucky 7. Now, will 7 check? Let's check it. What's 7 minus 3 under this radical? 4. So you get 2 plus the square root of 4 equals 4. When you plug this 7 right back in there for a. Does that make sense? 2 plus the square root of 4 is 4? Yes, it does, because we know that square root of 4 is 2. Yeah. All right, let's continue. What if they give me double radicals, Young? Radical equal to radical. Are you going to be shaking? Are you going to go, Mama, Mama? No, don't be shaking like that, because these are isolated, so you can square both sides. Well, check this one out. Square both sides and both square roots. Got 2 birds with 1 stone there. To coin a phrase, comes out. All right, so in this case, the squares knocked them both out, leaving me with what was underneath the radical. Nice, Young. So remember, here's a good equational review here. Letters left. Get those letters on the left to solve for x here, because we only have a first powered variable here, a linear equation. And add 7 to both sides. That's numbers right. And we end up with 5x minus x is 4x equals 17. Divide both sides by 4. And we have conquered yet another radical equation. X is 17 fourths, which would check if I plugged it in here. Take my word for it. All right, so now we're getting to the big league problems here. Let me look at the camera now. Again, the focus of this show, don't always just do the easy ones, Young. Do the toughest ones. And if you can do this next example here, find some in your book like it, you're going to be well on your way. Let's go to this one and show you why. All right, this one's almost got the whole course in it, one problem. If we take and square both sides, now we've got the square root by itself. Some of you say, well, I could divide the 4, but then you're going to have nasty fractions here. So I'm just going to take and square that whole thing. Square that whole thing. Now, what do you see here when I square this? Well, gee, Young, that's a FOIL problem. I get x plus 4 not once, but twice. All right, so the old FOIL is back. So if you want to write out FOIL here, x times x, x squared. The outside 2 terms is 4x plus 4x gives me plus 8x. 4 times 4 is plus 16, so all kinds of good stuff in this one. Equals, when I square this, what happens? Well, if I square the 4 inside here, I get 16. And when I square the square root, what happens? Oh, those arch enemies there wipe each other out. You just get the x plus 1 hopping right on out of there. All right, now notice in the first equations we had x to the first power. When I see that x square, I'm thinking, might be more than one answer to this one, Young. So I'm going to go ahead and distribute that 16 through, which will give me 16x plus 16. So we have x squared plus 8x plus 16 equals 16x plus 16 over here. All right. So we've got some FOILing going on. We've got taking out radicals. We've got some distribution going on. Now we're going to collect like terms. So to solve this, we got to get everything equal to 0 by bringing all of this to the left. How? Well, we're going to subtract the 16x and line up our x's with our x's. We're going to subtract 16 and line up our numbers with our numbers. And we're going to bring it down and have x squared minus 8x equals what? Our hero 0. So we have learned when we have a square involved, we want to use that 0 product principle and factor and get the 2 answers. So now we can factor. What do these two have in common? How do I factor this? I can take a common x out and put what's left in the old parentheses here, x times x minus 8 equals 0. So what's my 2 answers? What makes this 0 is one answer. What makes this 0 is the other answer. So the 2 answers, x equals 0 or x equals 8. All right. Now remember, when you get these 2 answers, do what? Check them in the original problem, because when you plug them back in and check them, that's the only way you can make sure. So let me go back here. Here's what we started with. Okay, x plus 4 equals 4 times x plus 1. Let's put 0 in here wherever we see an x. So I'm going to take Mr. 0 and plug him in. So 0 plus 4 then should equal 4 times 0 plus 1. Does that make sense? Why, sure, because 0 plus 1 under here is 1. Square root of 1 is 1 times 4 is 4 equals 4. 0 checks. So I guess on 0, for one answer, we'll put the happy face. All right, 8, let's plug it in. So wherever we see an x, 8 plus 4 then equals 4 times the square root of 8 plus 1. Square root of 8 plus 1 is 9. The square root of 9 is what under here? 3. So this is going to come out 4 times 3 equals 8 plus 4 is 12. So both of these answers are keepers. Now, are always this going to work? No, it won't always work, so don't go there. Don't go there. All right. So let me look back up at the camera here. Now, again, I've been beating you up with these radicals. I've been, you've been adding, subtracting, multiplying, foiling. We've been doing all kinds of things with them, Young. Where am I ever going to use this stuff? All right, let's go back to the graphic and we'll show you where you're going to use it. All right, so look at our friend, the Pythagorean theorem for right triangles. We've seen this in previous episodes. A squared plus B squared equals C squared on any right triangle. Remember those? All right, so you can use radicals with this to measure distances. All right, so remember the legs are sides A and B. They contain the right angle, and side C is the hypotenuse or long side of the right triangle. All right, so let me go back to the example here because I always want to stress where we're going to use this. When are we ever going to use this, Young, with radicals? Y'all never use it. So I picked my beautiful lake. I teach at the Palm Bay campus, and I've got a beautiful lake right out behind my classroom, and it's just an awesome view there. If you've never been to our campus, visit it. I mean, we've got a beautiful lake, and it's called Lake Titan. All right, so I'm going to use the Pythagorean theorem to measure the distance across Lake Titan here. And notice there, and this is how they measure things out in real life, A squared plus B squared equals C squared. All right, so what sides A, B, and C? Well, you have to recognize that A is 9 and B is 12 here, so I'm going to go ahead and plug in 9 squared plus 12 squared equals C squared. All right, and now going ahead and performing the math, 9 squared is 81, plus this one, 12 squared is 144, equals C squared. So let's see what that comes out. 81 there, I get C squared equals 225. All right, so without even getting our feet wet, like if you thought about it, you couldn't ask a person to stand here on the end of the lake with a tape measure and say, hey, we want to measure this distance, and go across here and go, all right, start walking, blah, 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 and get to the other side. Or think about sinkholes. You know, some of the counties have sinkholes, and they open up like that around homes, and they want to measure the distance. So what they do is they use the Pythagorean theorem, and they mark off distances around there in forms of a right triangle, or they can use the hypotenuse or one of the legs to get it. So you can really use this stuff out there in real life. All right, now looking down here, now Young, how am I going to solve for C? There's that C squared equals 225. Now, have we discussed something in algebra that attacks squares? Yes, square roots. So we could take the square root of both sides of that equation. To take out the square, hit it with the square root, and we could simplify the square root of 225, but I'm running down on time here, so I'll tell you that that's going to come out to be 15. So the distance across this part of the lake that I'm measuring is going to come out to be 15 yards. Tile guys use this all the time. I mean, architects, engineers, structures, and it all deals with the radical. See, so you can use this stuff in real life. Don't kid yourself and say you won't, all right? So to measure inaccessible distances, they will mark off right angles to it and use this nice Pythagorean theorem to get to the answer. All right, so in closing, remember what it takes to succeed in mathematics: effort, desire, motivation, and drive. Stay focused, pay attention to detail, always feel you can succeed. You will be surprised with the results. Take care, see you next time.